Okay, so hopefully this will be our last video on section 2.5. I know it's starting to wear on me, kind of like it's starting to wear on you guys. So, but um, here's the last couple of topics. The first one is called periodic functions. Periodic functions. All right, so we've got a coordinate plane here, and let's suppose that on this coordinate plane that we have this terminal angle. Okay, so our angle looks basically like this. All right, so and it has some point on it, AB. So this angle, we're going to say that this angle X here, the angle, we'll say that the angle from here to here has X radians. Okay, it's X radians. We don't know what it is. It's just some degree. Well, then since there are 2 pi radians in a whole complete revolution, there are 2 pi radians in this whole complete revolution. That means that x plus 2 pi, which would be this right here, x plus 2 pi would be this. If we went here and then all the way around again, that would be x plus 2 pi. So what that tells me is that the radian measure of x plus 2 pi also has that same point on its terminal side. So basically, here's what we can say from that. We can say this. We can say that b equals sine x equals the sine of x plus 2 pi, because those will have the exact same point on their terminal side. A equals cosine x. Same thing, the cosine. And we'll get more into periodic functions later, but this is just a general rule right here. Same thing, x plus 2 pi. Now here's the general rule that we can say. In general, we can say that sine x equals the sine of x plus 2k pi, where k is some integer multiple of 2 pi. So for instance, 2 pi, 4 pi, 6 pi, 8 pi, 100 pi. These are all multiples of 2 pi. Okay? Same thing for we can say the same thing for cosine. So all of these things would have the exact same answer, is basically what I'm telling you. Because the function is so periodic. So here is what we say. We say this. We say that a function is periodic. We say that a function is periodic if there exists some real number p such that f of x plus p equals f of x. If there exists some number p where this is true, then the function is periodic. We say that this is periodic. Okay? And that's for all x in the domain of f. If this is true, then there is a p-value, a smallest p, the smallest p that exists in this situation is called the period of f. For instance, in sine and cosine have the same period. The smallest such period that exists for sine and cosine is 2 pi. It's 2 pi. And we'll study more of this in detail next chapter. But here is here's a question. If cosine of x equals negative 0.0315, then what does the cosine of x plus 18 pi equal? Well, 18 pi is a multiple. That should say not 18x. This should say 18 pi. 18 pi is a multiple of 2 pi. And because of that, that means that it's going to go back around to the same point. So it would give you the same answer. Well, what if we change that to 2 pi would be the same answer. 100 pi would be the same answer. What if we change this up and said minus 2 pi? Well, it doesn't matter whether you add it or subtract it. That period is still going around. Even though you're going a different direction, it's still going around. And because the period is 2 pi, all those answers are going to be negative 0.0315, just like the answer. Because it just so happens that the k value, when we talked about 2k pi in the last slide, on the last page, the k value for this would just be negative 1. And negative 1 is still an integer. We want an integer k value. As long as it is an integer k value multiple of 2 pi, they're going to have the same answer. Okay? I hope that's understandable. Now, that's all we're going to get into with periodic functions at this time. Now, the page you want to make note of in your book, page 108. You need to go read this page. Everything in blue on this page is of utmost importance. These are called the fundamental identities. The fundamental identities. And so, with these fundamental identities, what we can do is we can use these to rearrange problems and simplify them, basically. Simplify the problems. So, the identities that we have is that cosecant x equals 1 over sine x, secant x equals 1 over cosine x, cotangent x equals 1 over tangent x, and these three are called reciprocal identities. Reciprocal identities. We also have on that page tangent x equals sine of x over cosine of x. Now, all these should make sense to you, and because think of what tangent is. Tangent is b over a. What is sine? Sine is b, cosine is a. Hopefully that makes sense. And they have the a over b form written on that page to show you. I'm just giving you these main forms because I know you can read and you don't want me to read it to you. So the other identities, we have the sine of negative x. That's the same thing as the negative sine of x. The cosine of x is the same thing as the cosine of negative x, negative x is the same thing as the cosine of x. And then the tangent of negative x is the same thing as the negative tangent of x. Same thing as the negative tangent of x. So, in the way we get these negatives and not negatives, well, think about this. Think about where sine is negative, where an angle would be negative for sine. Where would an angle be negative for sine? That would be where our answer of sine would be negative. Where would our cosine be negative? Well, the answer to that would be the same place where cosine is positive. And different things like that. You can look at it that way. They have some examples on there for you. We also have, and these are called negative identities. We also have something called the Pythagorean identity, and this is what it looks like. It's going to look very much like the Pythagorean theorem. Sine squared x plus cosine squared x equals 1. That's our Pythagorean identity. Now, I do want to mention something to you because I don't want you to get them confused. Sine squared x and cosine squared x, this applies to. Sine squared x is the same thing as sine of x squared. Okay, that's the same thing as that. However, the sine of x squared, now notice how this first one here, that's sine squared x. This is sine of x squared. Okay, but sine of x squared equals the sine of x squared. Notice these two, this applies to cosine as well. These two rules here are the most confused. So be careful as you're reading through these identities. I'm going to give you these on exam so you don't have to memorize them, but it's going to help you to know it if you memorize it. These are called the fundamental identities. They hold true for everything, basically. Okay? Angles in degree or radian measure. So what you're going to do is we're going to actually use this to simplify some problems. Okay? So, for instance, if I give you this, we're going to simplify each of these expressions using an identity. So if I give you this, sine squared x plus cosine squared x all over tangent x. Well, sine squared x plus cosine squared x, that's the Pythagorean identity, which equals 1. So really, this is 1 over tangent x. Well, what does 1 over tangent x equal? Well, using your reciprocal identity, 1 over tangent x is cotangent x. So you see what we're going to be using these identities for. Just take larger scale problems and simplify them to things that we can work with. It's much harder to work sine squared x plus cosine squared x over tangent x than it is just regular cotangent x. What about this one? The sine of negative x over the cosine of negative x. Well, sine of negative x over the cosine of negative x. Well, this is the same thing. Think back to your fundamental identities. What is sine over cosine? You got to memorize this. Sine over cosine, that's the same thing as tangent. So really what we're saying here is this is the tangent of negative x. Sine over cosine is the same thing as tangent. That's on your first blue words on page 108. Okay? Sine over cosine is the same thing as tangent. So what is the tangent of negative x? Well, our negative identities tell us that it is negative tangent x. Now, folks, this is the part of trig that I absolutely love, these identities. And we're going to pile more identities on top of more identities. And I know that scares you, but I'm giving you the identity sheet for test. I know that scares you, but please, folks, don't get overwhelmed with it. I love these, and you're going to have tons of them because I can't give you, there are an infinite number of these types of problems. I could give you 80 problems for homework, and that still would not cover it. So I'm going to give you a few identity problems, no more than what you've been doing. Let me address homework. Homework will not be more than what you've been doing. I mean, if anything, it may be a little less as we get more involved, okay? But you'll have a good, decent amount of homework just because of the nature of the beast of trig. It takes practice, okay? And so there are an infinite number of these. The only way you're going to get good at identities is through practicing and doing more and more and more and more of them. And if you don't get get them down now, it's going to hurt you the rest of this course. And if you're going to Cal 1, if you're going to be an engineer major, or you're going to calculus for another reason, if you don't get these identities down now, it's going to be serious when you get to calculus. Okay? So I'm just giving you a little forewarning. Memorize, well, you don't have to memorize them. Know how to use them, okay? And take them seriously. And every chance you have that I give you on homework to work an identity, work it. And even go to your book and look at the exercises at the end of the section and work those, because the odd number exercises are in the back of the book. So work those. The answers are. So work those and get practice. That's the only way to get good at the identities. This is all of section 2.5. Finally, I hope this video helps you. Have a good day.